Thanks for the introduction. So I'll be talking about biased linearity testing in the 1% regime. This is joint work with Subhash Khot. If you don't know what any of the words in the title means, that's fine. I'll explain everything one by one. Also, I'll try to give a relatively non-technical talk. So I hope everyone understands everything. And if there are any questions, feel free to stop me at any point. So first, let's see what the basic setup of the problem is. So I'll describe what the query model is. So throughout this talk, I'll have some unknown function f from 0, 1 to the n to minus 1, 1. And I'll have this convention that I'll always think of the inputs as 0, 1 valued and the outputs as minus 1, 1 valued. And this is just to simplify a lot of notation. And so you can think of f of x as something like minus 1 to the g of x, where g is like your usual Boolean function, which you might be like used to thinking about. And the goal is to test if f satisfies some property. And so, for example, the property we'll be most interested in this talk is that is f a linear function when viewed over f2. So what does a linear function look like? A linear function is a function of the form f of x is minus 1 to the sum ins of xi. So it's like a parity of some bits, and because I'm in minus 1, 1 notation, I'll do minus 1 to the power that for some s. And this function I would call as chi s, which is minus 1 to the sum ins xi. And what are we allowed? So we are allowed to query f at, say, some k points, x1 up till xk, which are chosen in some way, randomly or deterministically. And what we can do is we can ask the value of f at these k points. And so the model I have is I choose k points in some way, I give it to this black box, the black box returns me the k values. And finally, I want to say yes or no based on these values of all the x1 up till xk I'd chosen, and f of x1 so on up till f of xk. And the goal is usually to have correctness, and also we want k, which is the number of queries, to be as small as possible. So two very simple things to see here are the following. That firstly, usually deterministic queries are useless, because if like you choose k points, and for example, if these k points are chosen deterministically, the value of f at the other points could be arbitrary. And so essentially you're not testing any properties that could strongly depend on all the points in the hypercube. And the other thing I want to say is that the problem as stated is hard if you just want to test if f is like linear or not. So for example, suppose that you have a linear function and I change it at one of the 2 to the n points just arbitrarily. So any such test which makes k queries, unless k is like exponential, I won't even see that point. So it's essentially useless, or in the sense that such a test cannot correctly determine if f is linear or not. So the basic idea in such problems is to like change the goal, and the goal will be this problem of linearity testing. So I assume many of you have seen it, but I'm still going over it. So, and the goal is to distinguish between two cases. So the first case is that f is a linear function over f2, which is exactly what I said earlier, that f of x is some chi s for some s. And the second case is that f is far from a linear function. And what does far mean? So far means that for every linear function chi s, the number of points on which f and chi s disagree is at most 1% of all the 2 to the n points. So the way I'll write it is that the probability over the uniform distribution that f of x is not equal to chi s is at least 1%. Okay, and the model is the same. You choose some k queries in like the hypercube randomly, and you say yes or no based on these values, x1 up till xk and f of x1 up till f of xk. So a very classical test for this problem is one that was introduced by Blum, Luby, and Rubenfeld in the 90s. And the test proceeds as follows. It is like essentially the most natural thing you would try. And the test is the following. And the test is a 3-query test. And it proceeds as follows. So you choose 3 points x, y, and z in the hypercube, 0, 1 to the n, uniformly conditioned on the fact that x plus y plus z is the all zeros vector mod 2. So for example, one way to do it is to choose x and y uniformly and set z to be just the XOR of x and y. And then you query all of f of x, f of y, f of z. And then you test that the product of f of x, f of y, and f of z is equal to 1 or not. So something that is simple to check in this case is that in the first case, that suppose f is linear, such a test accepts with probability 1. And what you can do is you can just consider this expression f of x, f of y, f of z, and plug it into that -1 to the summation ins xi. So essentially you'll get -1 to the summation ins xi plus yi plus zi. And just by how the points are chosen, we know that x plus y plus z is 0, so you'll get 1. So this is the simple direction of the test. And what BLR prove is essentially soundness for the second point. So they prove that if the test accepts with probability 1 minus epsilon, where epsilon you can think of it as say 0.1, then f is O epsilon close to linear. So what that means is that there is some linear function chi s such that f and that linear function agree on something like 1 minus this O of epsilon fraction of the points of the hypercube. So you can see this statement as like a contrapositive of the second point I have mentioned above, which is that if f is now far from linear, then the test rejects with like significant probability. So, okay. Yeah. So I'll just restate exactly what the theorem is in the notation we'll follow, which is that suppose f is a Boolean function from 0, 1 to the end to -1, 1, such that the following is true, that the expectation of f of x, f of y, f of z is at least 1 minus epsilon, where x, y, and z are chosen from this distribution, which is from 0, 1 to the end, condition on x plus y plus z is 0. Then there exists a set S, which is a subset of like the first n integers, such that the expectation of f of x times chi s, which is like the correlation between f and this linear function, is at least 1 minus O of epsilon. Okay, so I guess before I go on, like, yeah, maybe I'll quickly, is there any question about what this theorem says? Okay, so I'll go on. And so this kind of a theorem is what I'll refer to as the 99% regime of the test. And the reason for that is that here I have this test acceptance probability, which is like close to 1 minus epsilon, which is like 99%. And essentially this theorem says is that if the test accepts with probability something like 99%, then the correlation between f and a linear function is maybe like 97%. Okay, so I hope everything up till here makes sense. And for this BLR test, what is also true is that the exact same test also works in what is called the 1% regime. So what that means is the following, is that, so let me just parse over the statement of the theorem once. It's exactly the same thing. So suppose f is a Boolean function. And now suppose the expectation of f of x, f of y, f of z is like epsilon. So this is suppose like 1%. Then you want to say that there is a linear function such that the correlation between f and that linear function is at least say epsilon over 10. So this is like saying, so if f was, for example, a random function, you would expect this quantity to be like very, very close to 0. So this is saying that under this test, if like a function deviates from like a random function in like a non-trivial way, then it must have this linear structure hidden somewhere. Okay, yeah. So this is what is called the 1% regime. And yeah, so there is, yeah, if you are interested in the proof of this, you can see like Ryan O'Donnell's book. It's like in the first chapter and it's like a very neat proof. Okay, so let me first say like what linearity testing like has been used for and where it comes up. So linearity testing is essentially one of the first places where people studied property testing, which is like robustly testing properties of functions. So for example, it's testing linearity here, and like now there are books and surveys on this. People study all kinds of properties about like graphs and like whatnot. And so the original motivation of BLR was to do like some kind of self-testing, self-correcting properties. So for example, suppose you have a black box which computes some linear function, like suppose it's computing matrix vector products. And in many such cases, you want to test if it is giving you the correct outputs. And so what becomes simpler for many of these functions is to first test whether it is at least close to a linear function, maybe not exactly what you want to compute. And so these kind of properties are very useful there. So the linearity testing problem exactly as I stated, so I won't go into why. It's like if you just parse the definitions, it's more or less the same as the local testability of the Hadamard code. And it's one of the very crucial ingredients in like the PCP theorem and is used in many hardness of approximation results. And it's also again one of the early uses of like Fourier analysis in theoretical computer science, where it gives like very neat proofs for things. And now this is like extensively used. Okay, so now I won't talk too much about applications, but I'll just try to extend the problem and okay, try to make it slightly harder. And the question is, what if we change the distribution? And now you might ask what it even means to change the distribution. And so we'll see that. So now I'll consider the problem, which is called p-biased linearity testing. So up until now, I've written exactly the same thing. So I have a function. I want to test if it is linear or if it is far from linear. So the only thing is that earlier I said that the probability that f is not the same as some linear function is at least 1%, which meant that it disagrees from this linear function on 1% of the points in the hypercube. But now this 1% you can think of comes from other distributions, and we'll consider one of the most natural other distributions, which is the p-bias distribution. So just to set some notation, so I'll always consider p less than half in this talk, and so everything, like almost everything I'll say holds for p more than half, but this is just simpler. And I'll consider the distribution on the hypercube, which is mu p. And mu p is the following distribution, which assigns probability p to 1 and 1 minus p to 0. And now a relevant distribution on 0, 1 to the n is just the point, like the product of this distribution on the n coordinates. And now I can ask exactly this problem of linearity testing, where I care about this quantity, but it's coming from this distribution mu p to the n. And I'll care about both the 1% and the 99% regimes, and we'll see what we know. Okay. So yeah, I hope the problem statement is clear. Okay. Yeah. So for this case, like, okay, so now we have the BLR test for p is equal to half. And what we want is, can we simply extend it to like the p case? And essentially you can. And so I'll propose like a candidate test, which is like the most natural thing you'll do. So I'll define a distribution nu on 3 bits, 0, 1 to the cube, which is defined as following. So I'll say x, y, and z are from this distribution nu as follows. So with probability 1 minus 2p, I'll set all of x, y, and z to be 0. And with probability 2p, I'll choose x, y, z to be uniform from this set of x plus y plus z, which is 0. So you can see that this distribution nu satisfies two properties. So firstly, that whatever the output from this distribution nu is, it always satisfies x plus y plus z is 0 mod 2. So because in the first case it's 0, and in the second case also it is 0. And also the marginal of each of these 3 bits x, y, and z is mu p. So for example, if you just see the marginal of x, what is the probability that x is 1? In the first case it is 0, in the second case it is half, and the second case occurs with probability 2p, so you get 2p times half, which is p. And so now once you have such a distribution, I'll also consider this distribution nu to the n, which is like the n-fold. So I'll just set some notation. So I'll say that x, y, and z are n bit vectors 0, 1 to the n, chosen from nu to the n in the following way. So I'll think of it as like a 3 cross n matrix, where x will be the first row, y will be the second row, z will be the third row, and the ith column will be chosen independently from nu for every I. So I hope the notation is clear, because yeah, like it'll always be in the background. And now once I have like this distribution, like I can naturally write a test, which is essentially the BLR test, with this being the corresponding distribution. So this is just a summary of everything I said till now. And the test will be like, given a function f, I choose x, y, z from nu to the n, and I query f at f of at x, y, and z, and I check if f of x times f of y times f of z is 1. So again, just note that because of the first property that x plus y plus z is 0 mod 2, essentially we always have that linear functions are accepted with probability 1. Yeah. And so now you might ask if like the soundness case also holds as in the BLR test. And the answer, okay, yeah. So yeah. So let me repeat this. If f is linear, we can see it is accepted with probability 1. In fact, it is true that if under the distribution mu p to the n, f agrees with like a linear function with probability something like 1 minus epsilon, then also the test accepts with probability something like 1 minus 3 epsilon, at least. So the reason is that because there are only 3 queries, you can union bound that all the 3 queries are coming from the relevant linear function. And so such tests are what are called like tolerant tests in like the literature, like under some parameters, but I won't go too much into that. Yeah. So what was proven by Dinur, Filmus, and Harsha is that the test works in the 99% regime. Essentially, that suppose the above test accepts with probability 1 minus epsilon, Then there is some set S such that the expectation of x from mu p to the n, f of x times chi of s, which is like the correlation between f and a linear function chi s, is something like 1 minus O of epsilon. So I'm slightly lying that they prove this, but I think for our purposes, it's not too big of a lie. Like they prove it under some things, but yeah, more or less this works. And yeah, I think none of the authors are here to catch me on it, so it's fine. So yeah. And I will just mention this other work by Kopati and Saraf, which also proves some other test in the 99% regime for like the p-bias linearity testing problem, but I won't go too much into that test for this talk. Okay. So I'll leave the slides for a minute before I get into more things. Okay. So now you might ask, like, this is like the most natural thing you would do. Does it work in the 1% regime as well? And like, this is the study of this talk. And I will give spoiler, which is that it fails. That like the most natural test you would think works, it fails actually. And when p is not equal to half, when p is half, this is the BLR test. And so before I talk more about this result, let me like just set up the framework. Yeah, so let me give you a general framework of linearity testing. So this was like this 3-query test, and I'll just extend it to general k queries. So what happens is I have a distribution nu now on 0 1 to the k. And I want the distribution to satisfy two properties. So the first is that x1 plus x2 so on up till plus xk is 0 mod 2. So this is that it's only supported on like these points which are like accepted by the linearity test. And the marginal of each of x1 up till xk is like mu p. So these are two conditions I would require from this distribution nu. And now similarly, I would define this distribution nu to the n, so which outputs k vectors in 0 1 to the n, where like you can think of it again as a k cross n matrix where each column is chosen independently from nu. So it's essentially like the same as what I had before, like the example. And now the test is very natural. So I'll call the test lin nu, which is that given a function f, essentially I would choose like k points from this distribution nu to the n, and I will query f of x1 so on up till f of xk, and I'll accept if and only if f of x1 times f of x2 so on up till the product till f of xk is equal to 1. And again, you can see that linear functions pass it with probability 1, like functions epsilon close to linear with pass with probability at least 1 minus say k times epsilon and things like this. Okay, so let's see what is known about upper bounds here for such kind of tests. So this is like the general framework. So the main result that was proven recently, and I don't think anything was essentially known before this result, was this work by Bhangle, Khot, and Minzer, which shows that if p is in like 1 by 3 to 1 over 2, then there is a 4-query test of the above form that works in the 1% regime. So I won't exactly state what this means because I just state like the more general form in the next slide. And they prove this as part of their like series of works on understanding approximability of satisfiable KCSPs, if this means anything. So extending their result, we prove like essentially using their techniques with like some new ingredients that if you have any p which is like at most half, and the number of queries you have is at least 1 plus 1 over p, then you have a k query test of the above form that works in the 1% regime. So essentially we have like a query upper bound that if k is at least, if like you have at least 1 plus 1 over p queries, then you're fine. And let me like for the sake of it exactly say what this means. It says that if you have any, so p and k which satisfy this property, then there exists such a distribution nu on k queries such that the following holds. So for any function f, if this expectation, which is expectation of f of x1, f of x2, so on up till f of xk, is at least epsilon, where these k queries are chosen from nu to the n, then you have a subset S such that the f of x times chi of s, like the expectation of this is at least some function delta of epsilon. So now we don't get like epsilon over 10, it's some horrible function of epsilon. But so again, like just to parse it in words, it's saying that if like this, wait, sorry. Yeah. if this expectation of f of x1 so on up till f of xk is at least epsilon. So this is, you can like think of saying that the test accepts with probability at least half plus epsilon. Then f has like correlation with the linear function, which is like at least like again some constant. Yeah. So now I'll also just state the lower bound we prove, which is like very tight. We say that if p is at most half and k is strictly less than 1 plus 1 over p, then no such test can work in the 1% regime, which is like essentially tight. And again, let me just formally say what it means. So if you don't exactly parse what like the formal thing means, it's fine. So now we say that if you have any p which is at most half and any distribution nu on 0, 1 to the k, where k is strictly less than 1 plus 1 over p, then the following is true. Then we can construct a function f based on the distribution, like a Boolean function, which satisfies two things. So firstly, that this correlation probability that expectation of f of x1, f of x2, so on up till f of xk is say 0.01. So the test accepts with probability like half plus epsilon. But for every s, it holds that if you consider this expectation of f of x times chi of s, this is like little of 1. So that's being hidden. Oh, yeah, yeah. So this is just, I'll say that this is f of x times chi s of x, and this is just little over 1. Oh, okay. Yeah. Yeah. So this is just saying that the correlation of f with any linear function is little over 1, whereas the test accepts with non-trivial probability. Oh, I think the maybe I can just use it. Yeah. So I'll just again state the theorem. We say that if k is at least 1 plus 1 over p, then such a k query test works. And if k is strictly less than this, then no such k query test can work in the 1% regime. And in particular, the 3 query test that I said earlier cannot work when p is not equal to half. No. So like there exists such a distribution. So yeah, this is the next thing. So in fact, what we show is that like the properties are stated above, like up to like some star, work if and so such a test works if and only if like the coordinates of the distribution nu are like pairwise independent. So essentially you have like k queries, if they're pairwise independent, like such a test works with these properties. And okay, this is also not exact, but like more or less this is the thing. And 1 plus 1 over p is like, this is a simple analysis, is the threshold for when such a distribution with pairwise independent coordinates can exist. So I'll just take the last 2 minutes to talk about some very simple problem in probability theory that we solve for this. And I think it's like the kind of thing I would like to have an oral proof, but I don't have an oral proof. It takes like 2-3 pages. So let me quickly go over this. So suppose you have two random variables, x and y, which are Gaussian 0-1 random variables. So then we know that the following are equivalent. So the first is that x and y are independent random variables. And the second is that for every nice functions f and g, the expectation of f of x times g of y equals the expectation of f of x times the expectation of g of y. So this is just basic probability theory. And now if you rearrange, this is like the same as saying that for every nice function f and g, whose individual expectations are 0, like the expectation of f is 0 and the expectation of g is 0, it holds that the expectation of f of x times g of y is 0. So this is simply because this expression I can write as expectation of f minus expectation f times g minus expectation g. And now I want to ask what happens with 3 random variables. So the first is the same, x, y, z are mutually independent, is the same as saying that for every nice f, g, and h, expectation of f of x times g of y times h of z equals like the product of the 3 expectations. But now let me ask this problem, which is that for every nice f, g, h, with expectation f, expectation g, expectation h all 0, it holds that the expectation of f of x times g of y times h of z is 0. Like what about this condition? So it is easy to see it's not the same as the above. So for example, suppose x is independent of y comma z and they are not mutually independent, then this expectation would be 0 because you can write it as the product of the expectation of f times the expectation of g times h. And essentially, what we prove is that this is tight, like the converse also holds here. So if this holds, then at least one thing like this should hold. So I'll just quickly state the theorem. So if you have k random variable, like k Gaussian variables, then the following are equivalent. So for every nice function f with expectation f0, it holds that this expectation is 0, which is the expectation of f of x1, f of x2, so on up till f of xk. And this is equivalent to saying that some coordinate I is independent of the remaining coordinates. And in fact, we don't even need like different functions fgh, like it works if you take like essentially the same function. So 2 implies 1 is like essentially obvious, like in 1 implies 2, I'm saying it also works if you take like the same function f. Yeah. And yeah, so this looks like exactly the expression in linearity testing, and this is like the connection.